All right, welcome. This video is going to talk to you about complex numbers and imaginary numbers. What you need to do first of all is have your calculator with you and try to prepare to solve these four quadratic equations on your calculator. Either use the quadratic formula or do it out by hand, but whatever method you want to try to do, see if you can work through them. If you could put the video on pause for right now, go through and fill in the answers to these three equations. They're all trying to have you solve it for x. All right? Now I'm back. Now that you've hopefully had a chance to solve through this one here, when you go through and you solve the first one, hopefully you used the quadratic formula and you got an answer of 0.5 and negative 4. So x equals 0.5 and negative 4. So if I were to ask you then, what are the roots of this first equation here, if it were to say y equals and I asked you to graph it, the roots would be 0.5 and negative 4. If you try to do the next one, you would hopefully factor this one, or you could use the quadratic formula. If you factored it, just to show you another way you could have done this, or I'm sorry, if you would have factored it, you would have had x plus 5, x plus 5, x plus 1, and then you would have had the roots of x equals, if it still equals 0, you'd have x equals negative 5 and negative 1. So those are the values for x that you could put in the equation to make the equation equal 0. And also those, if they were to say equals y here instead of 0, that you'd be finding the actual roots of that equation. In this one here, if you were to graph and solve this, or solve this for x, you would have hopefully used the quadratic formula for a, b, and c, where a is 1, b is 0, and c is negative 9. If you go through and solve that one, though, you'll get x equals 3 and negative 3. Okay? In other words, then, you could have also just basically added the 9 over to the right-hand side and then square rooted both sides, but you may have forgotten that there are actually two answers you can put in for x to get 0. It's positive 3 and negative 3. So again, if this were a parabola that shifts down 9 units, you would have then had to been, if I asked you to find the roots, the two roots would be 3 and negative 3. Well, let's try the next one here. Use the quadratic formula or whatever method you want to try, and you're going to hopefully solve this. Maybe possibly you might solve this one by saying subtract 4 over to the other side, and you say x equals, or x squared equals negative 4. But then when you go to square root it, your calculator is going to say something. Because the next step here is to take this and you're going to try to square root both sides and say x equals plus or minus the square root of negative 4. Now when I try that in my calculator, I want to try and see what that looks like. Let me just go through here and try it. I'll bring it over here to the screen. Here's my calculator, and I'll put it where the glare is not so bad. If I press the second square root negative 4, your calculator should probably say the same thing as mine. It says error, non-real answer. That does not mean, it doesn't say there's no answer, it just says that there's non-real answer. What that means then is that there is an answer to the question, but we have to first of all change the settings on our calculator. So let's go to our calculator now before we try to finish this problem. Change the settings on your calculator to go to the mode key, go down to where it says real numbers. It said error, let me change that again. It says error, non-real answer. So let's try to look at this next little option here, which is called complex numbers, where it's going to include not only the real numbers, but it's going to also include what are called complex numbers. And these complex numbers allow you to get around square rooting a negative number. So when you look at your calculator now and you actually try to solve this, now try to go back and do the square root of negative 4. If I go second square root negative 4 now, you're going to see that there's an actual answer to this problem. Okay? So in other words, the answer to this problem, when I say plus or minus the square root of negative 4, the answer to this is going to be x equals plus or minus 2i. So now you might be wondering to yourself, well, what is the meaning behind this 2i? Well, there was a mathematician by the name of Bombelli about 500 years ago that went through trying to get around how do you get past square rooting a negative value, and he came up with these numbers called complex numbers, which are also going to be a composition of a real number and an imaginary number. So when we say imaginary number, that's where this little I part comes from on the calculator and what we write down on our paper. So this I that you see here is the part that allows us to get around square rooting a negative number. Now, we really don't have any translation yet until we go to this next part here to figure out what is I actually equal to. So let's go back and use your calculator now and figure these things out here. If I ask you to solve this statement and solve the square root of negative 1, let's put that in our calculator now and put in the square root of negative 1, square root of negative 1, and then I put that in my calculator and hit equals, I get the letter I. So let's put that answer down and say that the square root of negative 1 equals I. Let's also now try to do the same thing with this next part and put that in your calculator. If you're wondering where the I button is in your calculator, there isn't a button, but it's actually right above the button. You'll see right above the period here, there's a little I button option here. So to get anytime you want to type the letter I, it's right above the period. Okay, you have to press second period to get to it. So let's type that in your calculator. I'll put this over here so you can see it. Put in I, or the second square root, I squared. So let's put I squared, second I, and then squared, close the parenthesis. And what that answer is also the exact same thing. So if I have two things that both mean the exact same thing, then you could probably make a relationship between these two things. All right? So then think to yourself, what is then the correlation between these two statements? If the square root of negative 1 equals I and the square root of I squared equals I, well then if I look at those two things, then I can say that the square root of negative 1 has to equal the square root of I squared, and if those two things are equal, then we can come to the conclusion that I squared equals negative 1. This is the one little conversion factor that helps you understand how to get from imaginary numbers or complex numbers to real numbers, numbers that don't have I in the answer. Okay? Let's try to look at this again, how it might apply to a quadratic equation. So let's go back up here to the top of this paper here now and look at, first of all, what are complex numbers? Okay? So if I want to think about what a complex number is, it's going to be the composition of two parts, a real number and an imaginary number. If you'll notice when you went to your calculator screen, you said the mode key, it says not just one number, it says the composition of a real number A and an imaginary number B. Okay, those two things together make up what are called complex numbers, but the B value by itself is the imaginary number. Okay, so when we talk about complex numbers and imaginary numbers, technically, if you say an imaginary number all by itself, it technically is a complex because then the A value would be a 0. All right, so when we talk about these complex numbers also, it's a combination of a real number and an imaginary number. Next, let's try to figure out what are the roots of this equation right here. In other words, then, if you're going to find roots like x-intercepts, you're going to be putting 0 in for y and trying to solve. Now, if we put 0 in for y and solve this, we're going to have 0 equals x squared minus 4x plus 5 equals 0. And then you're going to have to figure out some way to do it. Now, if you're going to try to factor it, you're trying to think of two numbers that multiply to give you positive 5 and add up to negative 4. Well, if you think about it, 5 is prime, and there aren't any two numbers that you can multiply to give you 5 and add up to negative 4. So then the next thing you might want to try, if you can't do it by factoring so easily, is to try to use the quadratic formula. But when I do the quadratic formula and put in x equals negative b, which is a positive 4, plus or minus the square root of b squared, which is 16, minus 4ac, you end up getting, inside the square root, a negative 4. Now, that causes a problem, because if your calculator was not in that mode, your calculator would then say error, non-real answer. But since we're now in the mode that considers other possibilities of roots that might work in the complex number system, let's finish moving forward then and allowing ourselves to square root negative 4. So if you can think to yourself, what does the square root of negative 4 equal? Put that in your calculator for a moment. What does the square root of negative 4 equal? Second square root, negative 4. That answer is 2i. Okay? Well, 2i then can replace this negative 4 that you see here, and your answer can look like this. So then I have 4 plus 2i, since the square root of negative 4 is 2i, divided by 2. Then the answer, when you finish reducing this, you can divide each of these by 2, and the answer is 2 plus or minus 2i. In other words, then, if I asked you what are the roots of this problem, there are two roots. One of them is 2 plus 2i, and the other root is 2 minus 2i. And then we would say then that this example here of this parabola that's in standard form has two complex roots, and it looks like this. Okay? Now, we got to think about actually what the situation is that makes it look like this. So let's go back and look at our other one that was a little bit easier that you did right at the beginning on that other page we just finished. So back here on this one, we said the actual answers to this problem were x was equal to plus or minus 2i. Now, why is that? When you look at the actual graph, we've up to this point thought roots were only x-intercepts. But now you can find that there are roots on complex roots now, because when I ask you what are the roots of this one, if I put 0 in for x, or 0 in for y, and solve for x, I'll have 0 equals x squared plus 4. But now when you solve this, this right here will then be, when I subtract the 4 over to this side, it'll be x squared equals negative 4. And again, the square root of negative 4 is 2i. So then we would say that the solution to this problem would have to be two roots. The roots would have to be plus or minus 2i. Now, we don't really have a coordinate system. This is the x-axis right here. This is the y-axis right here. Where is this 2i? So let's think about where that actually is in the graph and how these complex numbers actually look when we try to graph them. Now, when I try to graph x plus 4, y equals x plus 4 squared, now you have to be able to think three-dimensionally here. This right here, going this way, is the face of the xy coordinate system, okay? So when you look at this thing straight on, it's still the parabola that you are used to seeing when it's like this. It's the parabola of y equals x squared with the parabola opening up, like you see here, straight up and down, where you have your x-axis right here and your y-axis right here, right? But now if I turn it, look in more of a three-dimensional fashion, think of the Under Armour symbol, and you take the bottom part of the Under Armour symbol and you turn it twist it 90 degrees, so that you have one part of the horseshoe facing you, and one of the horseshoes facing flat and opening up, kind of like what we see here. So this is like an extra dimension to the xy plane that we're going to then make this be our imaginary axis, okay? So then when I say I have two answers to this problem, that I said the roots of this problem right here, when I said the roots were going to be plus or minus 2i and negative 2i, what you're actually thinking then, when you see it straight on, you're not going to see any roots because there's no actual x-intercepts. But you have to remember that every parabola has another opposite parabola in the opposite direction from the vertex. It's twisted and facing on the complex plane. So it's a little bit hard to get the concept of until you can actually see it three-dimensionally, and this is the best I can do for you. Another way to look at the same picture is to look at it from a top view. I'll zoom out so you can actually see this now. The top view, or I'm sorry, the front view is when you actually see it straight on like I had up here. When I had a straight on view, that's the front view. What you have to understand is that the front view actually shows you the parabola opening up, but then again, you have to think of it as the horseshoe, or the Under Armour symbol, the bottom part of it, twisted and coming out toward you and going away from you in the vertical direction. Another way to look at it is if you took this same graph here and you put your eyes over here and look straight at it like this, you're then going to see the lower half of the parabola, that's on the complex plane, going out away, and you're going to have from the side view, again, you're looking from this side, you're not going to see this part of the parabola because it's going to be parallel with the y-axis. So I have this extra bold here showing you that this is the actual part of the parabola that you don't see now because we're looking sideways at the complex plane where this is your y-axis and this is your imaginary axis and this is your y-axis, looking at it how you see here. Then the last thing is if I were to look at this from the top view, this could get a little confusing. If I were to look straight down like this, coming down on the top of this axis, you would then see two things crossing. You would see the parabola opening upward right here, and you would see the complex part of the parabola facing down, going down away from you. Okay, this is a little bit hard to try to grasp, this one here. But basically then this is the complex parabola that's twisted 90 degrees going down, and it's going to still hit the x-axis, or the imaginary axis, at plus or minus 2i. Now, to get some sense out of this then is when I try to do problems like I just did before, on this problem, this is going to be a parabola that does some shifting to the right, and then it would be up 1. If I were to graph this one, then it would also do the same exact thing. You just draw your picture of your parabola opening up, and then it would have another parabola opening down, and it would hit the complex plane at plus or minus 2i. Okay, the only way I can really show you this kind right now is with the graph like x plus 4 squared, or x squared plus 4, because it starts with the vertex right above and on top of the y-axis, or on the y-axis opening upward. And then again, if you twist the bottom half and open it downward, it hits the imaginary axis at plus or minus 2i. All right, now, this might be still a little confusing for you, but I think it'll make more sense to you as we move on and look at other examples. So let's look at some of these things here. When we get to roots like this, you're going to be asked to find some roots of different graphs. Now, with the understanding that you have so far is that you've been up to this point thinking that roots are just x-intercepts. But as we just got done showing you, that you can have a parabola that opens up like this or like this, and it can still have complex roots. Okay? So in this case here we have a parabola that has a vertex right on top of the x-axis, and you're asking yourself, well, how many do you see? How many roots do you see? Technically, there is one root at this point. Okay? But if we want to be more critical in our thinking about what that kind of root is we're going to call that a double root. Okay? A double root is a root that repeats twice. Now, what I mean by that is if I write the equation of this, it's going to be y equals x squared. Now, if you think about what that is that makes the vertex at 0, 0, it's because this does not shift anywhere. But if you were to write this out, you could also rewrite this expression as y equals x times x. It's the same thing where you put a 0 here or a 0 here. It's the same answer twice, so we call it a double root because there's two of them that are the exact same answer that you can put in either spot. To make better sense of that is here's another double root example as well. Let's make up something for this equation. This could be y equals x plus 1, I'm sorry, x minus 1 squared. Let me get that looking a little bit nicer here. We'll just leave it at that, but x minus 1 squared, if you were to take that then and write it in another form, you could also make it look like this, y equals x minus 1 times x minus 1, which is the same as x minus 1 squared, but if you want to think of it as when we say this is one root, a value that makes the graph equals, or the equation equals 0, the equation is this. The only number you can put in this equation that makes it equal 0 is the number 1. So we say that the root, or it has one root, and we would then be more critical and say that it is a double root. Okay? Now, moving on, that's one example of types of graphs that have one root, but we have a special name for them. They're called double roots. Okay? Now, in this case here, here's another example of a parabola that does touch the x-axis, and it touches it in two places. So we're going to ask you then, how many roots do you see in this picture? Well, this picture has two roots because you see it touching it in two places. Okay? So I would then say that this one has two roots. And if I were to be critical about those, they're both single roots because they're just, when you write out the equation, there's only one pair of parentheses that makes that x-intercept. For example, if this was going to be something like this, I could say it's x minus 1 times x minus 3, and I would have roots at positive 1 right here and positive 3. Okay? So that this one then has two roots. This one only has one. So to have one root so far, we would say that this is going to be one root, and it's a double root on the x-axis. Now, what gets confusing is we have to be even more critical about what we say as our answer because there are two types of roots. We have what are called real roots because real roots are made out of real numbers. So in other words, this has one real root, okay? And this one here is also one real root because it touches the x-axis in one place. This is going to be two real roots, okay, because it touches the x-axis in two places. Now we just got done talking about graphing parabolas that don't touch the x-axis. If I use the quadratic formula, like we had on this example right here, when we use the quadratic formula with this example right here, we worked through this equation right here and found that the two roots were 2 plus or minus 2i. You're going to have that happen every time you have a parabola that opens away from the x-axis like this one does and doesn't touch the x-axis. So then you'll see that you get there are still roots. You're going to come across the problem of the square root of a negative number in that parabola's equation when you try to use the quadratic formula, but then when you get plus or minus 2i, this has to have two answers every time because when you do the quadratic formula, it's once with a plus and a second time with a minus, and you're always going to have two plus or minus, or some number plus or minus another imaginary number, which creates two complex roots, okay? So to keep these things as simple as possible, whenever you see a parabola like this that's not touching the x-axis or opening toward the x-axis, you're then going to say it has two complex roots, okay? This example here as well, this example over here as well is another one. It can open up away from it or it can open down away from it. As long as it's opening up or down away from the x-axis, it's going to create two roots, but they're complex roots. So we're going to say two complex. Okay? So now you have to be changing your mindset to think, when we say we have roots, we have to now be more specific about the kind of roots we're talking about. When I say one root, or if I say a graph has two roots, it could be a graph that's touching the x-axis twice, or it could be one that has a parabola opening away from the x-axis and not touching it at all. So this kind, then, we have to say it has two real. The ones like this are going to have two complex. Okay? Now, one last thing is that it is possible to even have a triple root. An example of this cubic that you see here could be written like this: y equals x minus 3 cubed. Technically what that is it's y equals x minus 3 times x minus 3 times x minus 3. Okay? Now, when I ask you what are the roots to this equation, it is touching the x-axis, so it has to be a real root. And I ask you how many values or numbers you can put in this equation and get 0 for your answer. Well, there's only one. So to say that there's only one root, we're going to say it is one real root, like this, but we have to be more specific and say it's a triple root, okay? So the whole complete answer that you're going to say to this kind of graph, is to say that it is a one real root, but to specify also that it is a triple root because it's the same root 3 times in a row, okay? Now, as we make things just a little bit more complicated, this is as complicated as it's going to get, if you start making polynomials now, you have to be looking for bumps or parabola-looking type bumps that open away from the x-axis. Because as I just showed you here, you can have a bump that opens like this, or you can have a bump that does like this, that opens away from the x-axis, that makes a bump like you see here, opening away from the x-axis, creating 2 complex roots. Now this one, how would you define yourself how many different kinds of roots this one has? This one's going to touch the x-axis how many times? 2 times. So it has to have 2 real roots. Okay? Now, if it has 2 real roots, one of these is a single root. This one right here is a double root. So if I were to ask you what are the roots of this graph, what we'd like to do is to have you say that this is going to be, let's say it crosses the x-axis here at -2 and 1 at +1. You're going to say that the roots are -2 and +1, but then you need to specify that 1 is a, I don't have a space here, but that 1 is a double root. Okay? So after you say what the numbers are, while you're saying the numbers, we would like you to say what kind of root that is as you go through and define the kinds of, or when you list out the roots, to define that root, what kind it is. Okay? Let's look at this one right here, the next one. This one is going to have 1 real, and then also we have a parabola bump that you see here in the polynomial that has a bump opening away from the x-axis, okay? And this one here that opens away from the x-axis is going to be considered 2 complex roots. Every time you see a bump like this that you see like this, it's going to have 2 complex roots, okay? Now, you don't have to define these because when I say I have 1 real and 2 complex, these are all individual different roots. It's when you have repeating ones like we had here that are the same that we want you to specify triple root, double root, and so on, okay? So the most you're ever going to say is double or triple. We don't want to say quadruple or whatever. We're not going to take you into graphs that look like that in our book at least, so don't worry about that. So the only thing you have to really ever define is whenever you have a parabola or a cubic that is on the x-axis and it gives you 3 roots possibly, then you're going to say it has 3 roots, or that you have a triple root at that value, okay? Won't get any more complicated than that. All right, let's move on to the last part then. How do you work with the number I? Because we've been saying that these roots have, like that one we just had in that other example, had roots that look like this. There are times you're going to be working with roots that have I in them. You'll be multiplying them sometimes you'll be adding them, and so on. But first of all, let's look at how do you reduce an imaginary number that has powers other than just 1 or 2 as itself. From what we understand. So when you look at I to the first, we don't, with all numbers we look at with anything to the first power, it would equal itself, okay? When we look at I squared, we just said the definition at the very beginning here. We said the statement of what we can conclude, that I squared equals -1. So I already know that answer as well, that I squared equals -1. When you start trying to think about how could you figure out what I to the third is, well, I to the third is going to be a composition of the previous 2 statements. If I took I to the first times I to the second, you would then have an answer that equaled I to the third, right? But then if I also take what each of those equal, I to the first is I, I to the first equals I, and I squared is going to equal -1, then the answer when you take I times -1 is -I. That might have gotten you a little confused here, but basically what we're doing here is we're taking what we know prior to what we have by definition to make new statements. If I say I to the fourth, that little tail got a little out of hand, but I to the fourth is going to be the same as if you wanted to say I squared times I squared. Okay? Well, I squared is -1. If I take -1 times -1, you get +1. Now, if you keep watching and be critical of how I'm writing this here, you'll hopefully see a pattern. I to the fifth, I could take I to the fourth times I to the first. If I take 1 times I, The answer for I to the fifth then would have to be 1 times I, or I. I to the sixth could be a combination of I to the fourth and I squared. It could be a combination of I to the fifth times I to the first, because the exponents add up to 6. But the easiest one would be to say I to the fourth times I squared, which is 1 times negative 1, which then becomes negative 1. Okay? I to the seventh could be a combination of what I just said prior to this, which is negative 1, because I to the sixth times I to the first makes I to the seventh. There's lots of ways you can make the combinations to get I to the seventh, but an easy one would be I to the sixth times I to the first, which is then negative 1 times I, which is negative I. Now, if you start to look at the pattern here, you're going to start to notice that it makes a pattern, and it starts over each time, every 4 terms. Okay, so hopefully you're looking at this now. When I start here, or when I hit the 4th term, it's going to start over. It goes I, negative 1, negative I, positive 1. Then it goes I, negative 1, negative I, positive 1. So every 4 terms, you're going to see the pattern. Now, to make this a little bit easier, to figure out what I to the 100th is, or let's start a little simpler than that. Let's take I to the 20th. If it's repeating every 4 times, okay, then if you simply take 4 and divide it into the exponent, if it goes into it evenly, because 4 goes into 4 once, 4 goes into 8 twice evenly, there's no remainder, then the answer has to be a 1. Okay? If you try to do this in terms of decimals, let's say I try to do I to the 21st. Well, we know that that's the next one. Like if I to the 20th is 1 and I to the 8th is 1, then the pattern starts over for 21. You know the answer is going to be just I by itself, but to get the answer, if you take 21 and divide it by 4, the answer is going to equal 5.25. In other words, 4 goes into 21 5 times with a remainder of 1, and typically we would say that that's 1/4 or 0.25. But if you have a remainder of 1 or a decimal of 0.25, then the answer will always be I. When you take the exponent divided by, when you take the exponent divided by 4, if you get a 0.25 decimal, then the answer is going to be an I. Okay? So I'm just going to put this little statement up here that tells you to take the exponent and divide it by 4. Divide the exponent by 4. Then you can take these translations of anything that's I to any power and figure out then when you get a remainder or decimal of 0.25, the answer is I. Let's try I over here now to the 34th. And if you put 34 in your calculator, or just divide it in your head, 34 divided by 4, you're going to get 8.5. Well, a 0.5, when you divide by 4th, is 2/4 or 1/2. And what happens then is when you get a 0.5, that's because you have a remainder of 2 then left over, which would then have to be a negative 1. So if you get a decimal in your calculator, or when you divide of a 0.5, then the answer is going to be negative 1. And simply, if you have 0.75, or if you have no decimal, or if it goes into it evenly with no remainder, then the answer is 1. So now let's just try a couple more here on your own. You see if you can get the answer to these. If I have I to the 303rd power, what is the answer? You can pause the video now to try to see if you can get these. I to the, I don't know, let's make a number like 111. See if you can get that one also. Pause the video and see if you can get these right, and then we'll go over the answer here. All right? Okay, now that you've had a chance to go over this, hopefully you're going to get the answer to this. If you take 303 divided by 4, you're going to get 75.75. The remainder is 0.75, so then the answer has to be negative I. Okay? If I have this 111 here, the 111, if I take 111 divided by 4, you're going to have an answer of, let's see, 27.75. Again, 0.75 is negative I. So hopefully that makes it a little bit easier now to solve these. If you can figure out and memorize or know how to figure out the first 4 exponents with I, then you can find any exponent with I in it. Okay? Now the last thing is, if you happen to work with problems in your homework, which you will, how to evaluate problems like these, hopefully you have the translation again that I squared equals negative 1 when solving these. Okay? If you take I to the 3rd times 2I, that answer is going to be equal to 2I to the 4th. And again, recall that anything to the 4th power is 1, so this is going to turn into a 1, so the answer is going to be simply the number 2. Okay, if you want to be able to do this in your calculator, just to show you that there is a way to check your answers, again, the I character is right above the period, And you're going to have to do that one by going second I. Well, I'll do that first of all. If I want to do the I to the third part, I'll type this in like this, I to the third, so second I, exponent 3, and then square, or no, to the third power, like that. Oh, no, I did it twice, I'm sorry. Let me do that again. If I say 3I to the, hang on. If I want to do the first problem here, I'm going to do I to the third, and then I'm going to take that times 2I, like this. I'm doing the first problem again. Press enter, and you're going to get the answer 2, just to prove to you that that's how you can check your answer. To do the next one, if you cube 3I squared, if you take 3I and cube it, then you have to cube the 3 and you cube the I, and you're going to get 27I to the third. Well, what does I to the third equal? I to the third is negative I. So if you want to look at it this way then, I'll change this 27I, this 3I cubed, then I'm going to reduce it from 27I cubed into 27, that's negative I, and then I'll take that negative 27I times the 2I, doubling that makes negative 54I squared. But then I squared turns into negative 1, so if I have a negative I squared, that becomes a negative 1 here times a negative here, which is positive, and I would get the answer 54. Now you may not have taken that same route that I did to get the answer, but when working through this on your calculator just to verify your answers, just basically type it in as 27, like you see here, 27I squared, or I to the third power, let's see here, exponent 3, and then times 2I, like you see here, then hit enter, and the answer again checks out that it's 54. Now hopefully you're going to have success as you go through the problems in the homework, realizing that there are graphs of equations that have complex roots when you solve some of the quadratic equation problems, finding out that they actually have graphs that hit the complex plane axis, or the imaginary axis at different values, and they're going to have positive and negative, possibly roots like this that were positive 2I and negative 2I. Even though whenever you get an answer that does have an I in it, you can conclude, though, at least if you do the quadratic formula and you get something with I in it, you can conclude that this parabola will never touch the x-axis. Because if you have two complex roots, you can never have additional real roots with it, okay, if it's a parabola. Okay? And then the last thing I want you to pull away from this is that when you saw the different kinds of graphs, that you are critical about the kinds of roots that there are. Let me see if I can find the sheet I'm looking for here. That when you have a graph like this that touches the graph one time, it is one real root, because it's considering whenever it does touch the x-axis, it's a real root. Whenever it touches the x-axis twice, we'd have two real roots. When it doesn't touch it at all, they always come in pairs, okay? You'll always have an even number of complex roots, no matter what kind of polynomial you have. But parabolas, again, can only make as many as two complex roots. One thing you might be noticing, too, is that you'll never have more roots than the degree of the polynomial that you're working with. This is a parabola, also degree 2, and it can only have no more than two complex roots, okay? This one right here is a cubic. We say it is one real root, technically, but to cover all your roots, it is a triple root, okay? Again, a root is a value that you put in the equation to get 0 for your answer. There is only one number. This would be the number 3 for this answer here. But 3, the way you'd write the answer to this properly would be, we'll say the root equals 3, but then I want you to have a defining statement that it is a triple root. All right? And basically now from here out, when you see roots, we want to have you be more specific about what kind of root it is and if it is a double or triple root. Okay? Good luck, and hopefully your homework goes a little smoother, and hopefully this video helps.